Yes.
Okay, so let's begin. Last time we defined the Cartesian product of two sets, which is just, simply speaking, that is the set of all possible pairs of elements where the first element comes from A and the second one comes from B. Of course, this notation is not too precise that because here we here there is no indication where from xy comes. We know that it is possible to make it better in accordance with our second set construction principle. So that is a set of all subsets of P of A union B, which subsets are pairs. So that is a pair of X and Y for some X from A and some Y from B. So, but it's interesting to consider various subsets of A times B. The subsets are very important for mathematics because they allow us to model so-called binary relations, which are widespread. Now, let's get some abstract perspective uh, on these binary relations. So by definition, R is a binary relation. It's possible to define binary relation without any parameter, but it would make our exposition a little bit more complicated. So we avoid this possibility. I is a binary relation between sets A and B. So we don't speak about a binary relation, but a binary relation between sets A and B. If A is just a subset of A times B. So a binary relation between A and B is any subset of A times B, any set of pairs, probably say possibly say empty, any set of pairs where the first coordinates, whose first coordinates come from A and whose second coordinates come from B. Is it clear? Dear students.
Yes, it's clear.
So let's continue our definition, and for each binary relation, we define its domain, and its range. These are two sets, its range. So its domain is a set of all elements which really are first coordinates of the pairs in R. So this is a set of all such x's. Where from? From A, of course, uh, such that for some y, x, y is an element of R. And range is a dual concept. So this is a set of all second coordinates of our pairs. And if we take these two together, we will obtain so-called field, the field of relation R. That is the set of elements which are either first or second coordinates of some pair in R. Of course, it's quite clear that the field is a subset of A union B. And now, and of course, this is a subset of A. For we take just elements of A, not all elements in general, but some elements. And this is a subset of B. And now let's make our presentation not that abstract and give an example. Okay. First of all, let's define, let's take some A and some B. Let A be 0, 2, pi. Do you know the number pi?
Of course.
Why not? And also let's consider our university here. Why not? And the set B consists of 1, 3, say the square root of 2, the square root of 3, and say, I don't know, MIPT. Do you know what MIPT stands for?
Yeah, sure.
Of course.
Yes.
Okay. Okay. So let's consider these two sets. So here we suppose, of course, that HSE and MIPT are some sets, but in general it doesn't matter. So now we want to consider the following binary relation between these two. Say 0 square root of 2, 0, 3, 2, 3, HSE 1 and say 0 MIPT. Okay, is it clear that this set is a subset of A times B?
Yes.
So it is a binary relation. Is a binary relation. I will omit this word binary for in the nearest future. I don't want to consider any other relations. So I is a relation between A and B. Okay. What is the domain of A? So the domain is a set of all first coordinates, the set of all elements x from A, which has some pair, some y, so that xy belongs to A. So let's find all the elements of the domain. Is 0 an element of the domain?
Yes.
Yes.
Of course, 0 is. 0 is an element. And what about 2? 2 is an element. What else?
Well, HSE and 0.
But
Well, it,
0 has already been taken into account. So the domain is just 0, 2, and HSE, which is a subset of A, but which doesn't equal A. Is it clear?
Mhm.
What is the range? The range is a set of all second coordinates. So here we have the square root of 2, 3, 1, MIPT. So it is just that. 3, 1, MIPT. So, and we see that this is a subset, a proper subset that is not equal to B, a proper subset of the set A. And what is the field of this relation? The field is a set of all elements which are either second or first coordinates in some pair. So please, what is the field? The field is just the union of domain and range.
Yes.
So please, help me.
Okay, it's 0, 1, 2, 3,
Mm-hmm.
square root of 2,
Mm-hmm.
HSE, and MIPT.
Mm-hmm. Okay, that's it. For every finite relation, we may draw a diagram of it. We may draw a diagram. What is a diagram? Of course, formally, diagram is almost the same as the relation itself. But informally, the diagram is some drawing which might help us make the relation more vivid. Okay, what is the main idea? Let's draw some points in our plane, namely all points from the field, or maybe all points from A union B. It doesn't matter much. So HSE, MIPT, and now let's draw an arrow from one point to another one, if and only if this first point is the first coordinate of a pair, of which the second one is the second coordinate. So we have the pair 0, the square root of 2. So we will make such an arrow. We have pair 0, 3. We have pair 2, 3. We have the pair HSE 1, HSE 1, and we have the pair 0 MIPT. If you are to show more than one relation on in one diagram, you will mark this the respective arrows with some letter for your relation. Is the principle clear?
Yes.
So I think it is quite clear. What is a diagram? Diagrams are very useful when you're tinkering with binary relations. So any questions up to this point?
Not
So
yet.
on the diagram, we should draw all the possible relations, like
No. For each relation, you draw its own diagram. This is a diagram of A. But of course, in general, in principle, you should draw all the arrows for every pair that is. It's not possible to do in the infinite case, in an infinite case, but please pay your attention that diagram is an informal notion. You may make it formal, but then there will be no difference between the diagram and the relation itself. So is it clear?
yes.
So for R, we randomly choose a different, like,
why randomly? Why randomly? We have some definition for A, and we draw the arrows for these pairs.
Yeah, but I'm asking why, for example, in R we don't have I don't know, pi and 3 relation.
Pair, you mean?
Pair, yeah, pair.
Why don't we have pi 3 here? Because we have defined R this particular way. This is a
Okay.
definition for R. Why R is such? Because we want it to be such.
Okay, no problem. So I just want to...
This is a definition. You type it typically in mathematics. You don't argue with definitions, because arguing with definitions might be useful, but only in some philosophical perspective. This is not part of mathematics. Okay. So three more formal examples. The empty set is a binary relation between A and B. Do you agree? The empty set is a subset of every set and a subset of A times B as well. So do you agree that the empty set is a binary relation?
Yes.
Yes.
Why
Maybe.
not? Why not? Of course. A times B. A times B is a relation between A and B. Do you agree? So you may take all possible arrows, all possible pairs. And the last example is most important here, is as follows. First of all, let's give a definition. We say that R is a binary relation on the set A, not the, by the way, on a set A, is a binary relation on a set A, not between, if I is a relation between A and A. So a binary relation on some set is just a set of pairs where both the coordinates come from A. Is it clear?
Yes.
Yes.
As an example, let's consider a very important from an algebraical point of view relation, so-called identity relation, IDA. Okay, the identity relation for or of A. The identity relation consists of all possible pairs where the first and the second coordinates are the same. Is it clear? Of course, it is a subset of A times A. Let A be 1, 2, 3. What is the identity relation for A?
1, 1, 2, 2, 3, 3.
1, 1, 2, 2, 3, 3. Is it clear?
Yes.
What is the diagram? Here we have a few loops. Is it clear?
Yes.
What is the domain of the identity relation?
1, 2, 3.
And in general,
A.
it is just A, both the domain and the range. Is it clear?
Yes.
Yes.
Okay. Another example of a binary relation is an infinite one. Less than our usual less than is a binary relation on the set of, say, natural numbers. So the ordering, and in fact, any ordering is a binary relation. The ordering of naturals, the natural ordering of naturals is a binary relation. It is defined or better described the following way. It is a set of all pairs Mn such that M is less than whatever it means. M is less than N. For example, we may say that 2, 3 is an element of this relation. Is it clear?
Yes.
Yes.
Is 3, 2 an element of this relation?
No.
No, for 3 is no less than 2. And what about 3, 3? Is it an element or not?
No.
No. So if you try to draw the diagram for this relation, you will discover that it is infinite. So it's not possible to make such drawing in any finite time. So less than is a typical binary relation. And now let's introduce some convenient notation. In general, you say that 2 is less than 3 instead of writing that the pair 2, 3 is an element of less than. By the way, this symbol is now the name of a set. Everything is a set, and less than is also a set of pairs. So instead of writing 2, 3 is an element of the set, you just write 2 less than 3. Is it clear?
Yes.
And in general, I will apply the following convention. X, R, Y will stand for X, Y being an element of R. In general, I will use such notation. You see that it is 4 symbols shorter. 4 symbols shorter, and in most contexts, it is more clear. Any questions, dear students?
No.
About the identity relation for A, may I ask a question?
So please.
Well, will it be an identity relation for A, which is equal, for example, 1, 2, and for example, 1, 3, 1, 1? Is it also an identity relation, right?
If it has a pair 1, 2, it can't be an identity relation for as 1 is not equal to 2.
So the okay, now I got it. Okay, thank you.
Okay, and now let's consider some algebraical properties of binary relations. These properties are quite interesting, and also they are very useful in formal treatment of various concepts. The first of these is so-called converse relation. Let R be a relation between A and B. The converse, not inverse. By the way, they use also the word inverse here, but it is somewhat worse, as it has some unneeded and, of course, unwanted connotations. The converse relation of R is just R to the power minus 1. The converse of R is just the set of all pairs Y X, where Y comes from B and X comes from A, such that SOAP is who has a good intuition. What do they mean by
The pair XY, maybe it
XY
belongs to
is an
the
element of R, of course. So you just overturn every pair in R. As an example, if R was just 1, 2, 2, 2, and 3, 5, the converse is what?
2, 1, 2, 2, and 5, 3.
So diagram wise, excuse me. Diagram wise, you just change the direction of every arrow. By the way, there is no need to change the direction of a loop. Is it clear?
yes.
By the way, what is the domain of the converse relation? What are the ends of our arrows?
It is the range of R.
The range of R, of course. The ends of converse arrows are just the beginnings of the direct arrows, so to say, and the range of R converse.
Is the domain of R.
Surely, is it clear?
Yes.
Okay. Two more examples. What if you take the converse of identity? You know, the identity relation consists of all pairs where the first and the second coordinates are the same. That is the set of all possible loops.
It won't change anything.
Of course, every loop is, as a mathematician would say, invariant under this conversion. Is it clear?
Yes.
And what if you take less than and convert it? It would be?
More or equal.
No! This was a trap. No, it is just greater than. Greater than. You know, x is xy belongs to this one. If and only if yx belongs to this one. So, you know, is just y is less than x, but y is less than x if and only if x is greater than y. Is it clear?
Yes, yes.
No. Not the converse. Not greater or equal. And if you take less or equal as a binary relation, the converse of it is just what?
Greater than or equal to.
Of course. Is it clear?
Yes.
And now let's prove some general properties. Lemma 1. For every P and Q, which are some binary relations, the following is applicable. First, the converse of the converse equals the original relation. The converse of the union equals, so please, any ideas?
Intersection of converses.
Of course not.
Union of
Please
converses.
pay attention to the fact that conversion is monotone. That is, the conversion of larger set is larger. So it does not change the union for intersection. It is not like complement. The conversion is not complement. So please take
Okay, I see. Yeah.
take it into account. Okay, first let's prove our properties. We know that every element of our A times B is uniquely representable as a pair, so no need to do our routine such that take some arbitrary z. We know that every z is of the form xy, and these x and y are uniquely determined from z. So let's consider pairs from the very beginning. What does it mean that xy belongs to this set? When it is so? If and only if, by the definition, yx belongs to
R inverse.
the converse of p.
Yes, converse. Yeah.
It is not r, by the way. And when yx belongs to the converse of p, or p converse,
When xy
belongs to p.
belongs
So
to-
you know that a pair belongs to this set if and only if it belongs to this one. Hence, these sets are equal. You know, two sets are equal if and only if the elements are the same. And here we have proved just that. Is it clear?
Yes.
Yes.
Okay. And now let's prove the second statement. What does it mean that xy belongs to the converse of the union? That means that yx belongs to what?
Just the union.
P union q, of course, which is just either yx belongs to p or yx belongs to q. Do you remember our newly introduced notation that a r b is just a, the pair a b is an element of r?
Yeah.
Okay, but what does it mean that yx belongs to p? It is the same as xy belongs to the students.
The converse.
The converse of p, of course. It's a piece of cake. It's very, very easy. So that means that xy belongs to the union of two converse relations. Is it clear?
Yes.
We prove that xy just an element, and in this case we can say only that converse of p union q it's a subset of union p converse.
No, why? Why? Every step is an equivalence. So for each x and y, I see that xy is an element of this set if and only if xy is an element of this one. So y just subset? It is symmetric. So this equals This one. Isn't it clear?
But we considered only elements from first set, but what about the case
No,
if in
no,
first
no.
case
We
there are
have,
less elements?
informally speaking, we have considered all possible pairs from B times A. Have you, did you notice that here we have equivalences? Every pair from B times A belongs to this set if and only if. If and only if. If and only if means equality for the respective sets. Isn't it clear?
Okay, it's clear.
We have proved that every element belongs to the first set if and only if it belongs to the second one. You may easily start from this point and converse every implication here. Then you will see, you will obtain the same result. If this one is true, then this one is true. Then this one, and finally this one. Isn't it clear?
Okay.
Okay, so we have these two results, and as a corollary, let's formally prove that our conversion operation is monotone. That is, if P is a subset of Q, then the conversed relation of P is a subset of Q converse. It's very easy to prove now, as from P being subset of Q, I may conclude that the union of these two equals what?
Q.
It equals Q, so we know that equal sets behave identically, then the converse of the union equals the converse of Q. While by our lemma, this is just the converse of P union the converse of Q. So I see that these two sets are equal. That means that P conversed is a subset of Q conversed. Is it clear? As the union equals Q conversed. We know that always A is a subset, alpha is a subset of beta if and only if the union equals beta. Do you agree?
Yeah.
Okay. And now, let's consider another operation. By the way, dear students, binary relations are sets. So you may take a union of two relations, or even you may consider the complement, say, if P is a subset of A times B, the relation between A and B, you may consider the complement, which is just A times B minus P. Is it clear?
Yes.
By the way, if you consider less than as a relation on the set of naturals, what is the complement of less than? What does it mean that xy is not less than, x is not less than y?
Union of greater identity.
That means that xy, if x is not less than y, then x is greater or equal than y.
So it's the n by n minus less than.
It is just greater or equal relation. Is it clear?
Yes.
And the complement is something familiar. We have already considered it, but now let's consider some new operation, which is called the composition. Oh, it is a little bit trickier. Let P and Q be some binary relations. By definition, the composition of P and Q in that order, the composition of P and Q is just the set of all pairs X, and let it be Z, XZ, where X comes from the domain of P and Z comes from the range of Q, such that for some Y we have X, P, Y, and Y, Q, Z. Or schematically, diagram-wise, we have the following. What does it mean? That there is an arrow, a composition arrow from X to Z. That means that it is possible to go to Z in 2 steps via a path of 2 arrows. First by P, then via some intermediate station Y to Z. So X P composition QZ means nothing else than the following statement. There is a 2-arrow path, first by P, then by Q, leading from X to Z. Is it clear?
Yes.
Okay, let's compute some compositions. But first of all, let's make some observation. If P is the relation between A and B, and Q is the relation between B and C, then of course the composition is a relation between what? It is between domain of P and range of Q, that is between A and C. It is quite clear. As P always leads us from A to B, and Q always leads us from B to C, then the composition always leads us from A to C. Is it clear?
Yeah.
By the way, dear students, why have I written Q first and P second? Despite the fact that first we are going via P and then via Q. Why is it so strange?
Because we apply Q to the result of P.
Something like that. Something like that.
Vice versa.
For example, do you remember the calculus? What was the definition for the composition of 2 functions?
Well, it was G of f of x.
Of course, the value of the composition at the point x is just g of f of x. So something like that. First acts f, and then acts g. That means that we are applying f composition g to x Is it clear? So we want to be in a good accord with the composition of functions, as we shall soon realize that a function is a binary relation of some special form. Nothing else than that. Okay. Now, let's see some examples. The first example, let I be, say, 1, 2, 2, 2, and say 2, 3. The diagram is as follows. From 1, we may go to 2. From 2, either to 2 or where to?
To 3.
To 3. Okay. But what is the composition? Which points are connected by a 2-arrow path? Is it possible to go, say, from 1 to 1 via a 2-arrow path?
No, we can only go from 1 to 3.
But where can we go from 1 via a 2-arrow path? From 1
To 3
To 2
and
and
to
3.
2.
to 3, of course, as we have this path, and also to 2, as we have an arrow from 2 to 2.
And from 2 to 3.
So from 1, we can go to 2 and to 3. From 2
To 3 and to 2 as well.
to 2 as well, because of course it is possible to traverse our loop twice. Of course, it is well possible. Also, we may go from 2 to 3. So 2, 3. And can we go somewhere from 3? Can we go anywhere?
No.
So we have the following for our composition. Is it clear?
Yes.
So let's remember that a pair is in P composition Q if and only if there is a 2-arrow path from X to Z, first by P, then by Q. This is like traveling with a change. First you travel by, say, train, then, say, by plane. Is it clear?
Yes.
Now let's prove some general properties. So the composition is associative. So associativity, the associativity law for composition. Composition, so this composition equals this one. It doesn't matter which order of, it doesn't matter how you group the brackets. Is the statement clear? As a statement, the statement itself, not the proof.
Yes, it's clear.
Okay, And now let's prove it. What does it mean that XW belongs to this set? That means that there is what? There is a two arrow path with some change point called Z, so that X, Z belongs to what? Hey, dear students, belongs to
Position
what?
of Q and R.
Of P and Q, and Z W belongs to A. Is it clear? Is it clear or not?
Yes.
Okay, and now let's unfold this one. So that means that there exists Y, so that X, P, Y, and Y, Q, Z. Is it clear?
Yes.
And now let's do some basic logic. First of all, does this one depend on Y? This statement.
No.
No, it doesn't. So I may move it out. Move it out so this quantifier may be easily applicable also to this one. So there exists Z, there exists Y, so that X, P, Y, and Y, Q, Z, and Z, R, W. It's possible because this thing does not depend on Y. If I say that there exists X, such that X is even and today is Thursday, it is the same logically as saying that today is Thursday and there exists an X which is even. Is it clear?
Yeah.
Also, I may change the order of quantifiers. Why not after all? Why not after all? Because they are both universal quantifiers. And now I'll group these two together. Is it clear?
Yes.
And now I may observe that this one does not depend on Z. So I may easily move this quantifier here, which will result in the following. There exists Y such that X, P, Y, and there exists Z such that Y, Q, Z, and Z are W. Is it clear?
Yes.
And here I have what? Here I have just the statement that says that there is a two arrow path from Y to W. Y some Z. YW belongs to this one. So that means that from X to W, I may travel first by P and then by this composition. So I see that my pair belongs to this set if and only if it belongs to this one. Hence, this composition equals this one, as they have the same elements. Is it clear?
Yes.
Yes.
Okay, dear students, and another statement is about the converse of the composition. Another theorem. So the composition converse or conversed. This sounds better. What is the converse for the composition? What do you think? Use your intuition.
It is converse of P, composition converse of Q.
Aha! That the composition of converses in the reverse order. By the way, do you have matrices in other courses?
Yes.
Of course.
And do you remember what is the transpose of the product of two matrices?
It's P transpose times A transpose.
Exactly the same. Do you have inverse matrices?
Yes.
And what is the inverse of the product of two matrices?
P inverse times A inverse.
We see the same law. The same law. Don't you agree?
Yes.
So there is a clear algebraical analogy. Okay. And now let's prove it. What does it mean? We want to prove that these two sets have the same elements. What does it mean that xz is an element of this relation? That means what? That zx is an element of what?
Q composition P.
That is, there exists y, so that z p y and
Y, Q, Z.
x.
Oh, X.
YQX. We are going from Z to X. Ha! And now let's overturn this pair. That is just Z, Y, P converse Z, and X, Q converse Y. Is it clear?
Yes.
Well, now let's change the order of members in our conjunction. Clearly, they're logically equivalent. And now I see that means that there is a path, a two arrow path from X to Z via Y, first by Q conversed and then by P conversed. That is, from X to Z, it's possible to travel first by Q conversed, then by P conversed. So these two are equal, as they have exactly same elements. Is it clear, dear students?
Yes.
Okay. And now something else. What if you take, what if P is, say, from A to B, between A and B? What if you consider the following relation? What should it be?
P.
It is just P. And equivalently, dually, this is still P. How is it possible to prove it? Let's prove. What does it mean that XY belongs to this set? It means that there exists Y. So that there exists Z such that X Z belongs to the identity relation and ZPY. Do you agree?
Yes.
But when xz belongs to the identity relation, when x and z are identical, so there exists z which equals x, and there is an arrow from z to y. When this is possible?
When x and y belongs to p.
Of course, when there is an arrow, p arrow from x to y. Indeed, if it is so, then you see that zz equals x. So zpy means xpy. Equal sets behave identically. And for the other direction, if xpy, you may take what for that? Just what? Just x. Is x equal to x?
Yes.
Of course, you may take x as z. Is it clear? Is it clear, dear students?
Yes.
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 But please be careful. Be careful. In general, this composition is not equal to identity. Not this one. Not this one. In general, this converse is not the inverse with respect to our composition. It would be true only for some special class of relations. Is it clear?
Yes.
And my last notion is so-called image and pre-image. Let's consider the following drawing. Assume that we have some binary relation R between A and B. So it may include some arrows. It may have some arrows. Why not? And what if I take some set X, not necessarily a subset of A? And what if I want to consider only I want to consider the endings of arrows which have their beginning in X? Where the arrows which begin in X end? So what are their endings? If the beginning is in X, then the ending is what? This one, and also this one. Is it clear?
Yes.
So in general, I may define the following concept, which is read the following way. The image of X with respect to or under A. The image of X under A is the set of all points B from the range of A. They come from the range of A, such that there exists some A where in X, so that A are B. So these are just the endings of arrows which begin in X. Is it clear?
X is a set.
Of course, everything is a set. Is it clear?
Yes.
Can you please write an example?
Here is an example, but let's be more specific. Let I be, say, 0, 1, 0, 2, 1, 3, 5, 3, 5, 4. What is the image of, say, 0, 1, and 2? This is a set of all second coordinates of pairs, where the first coordinate comes from this set. Okay, first of all, let's find all the pairs where the first coordinate comes from this X. This pair, this pair, this one, and that's all. Is it clear?
Yes.
What are the respective second coordinates? 0, 2, and 3. So it 1, 2, and 3. So it is just 1, 2, and 3. Is it clear?
Yeah, thank you.
Yes.
So you may say something like that. Informally, this is the set of points. The set of points are accessible. Double C. Accessible from X. Accessible, that means that via one arrow path. Is it clear?
Yes.
Let's compare this definition with that of the range. What is the range of our R? The range is a set of all elements from B, from capital B, such that for some A, I, B. So this is the set of all second coordinates. While this one is a somewhat restricted set of second coordinates. So this is the set of all second coordinates of the pairs where the first coordinate comes from our X. So this is just the a subset of the range. Is it clear?
Yeah.
Is it possible? Is it possible to define the range as the image? The range is the image of what? Range of I is the image of
A.
Of the domain of
Domain.
A. Of A. Is it clear?
Yes.
So this is the image of X under A. A dual concept, which is much feared by students, so-called pre-image. What is the pre-image? The pre-image, or in Russian, прообраз, the pre-image of X under A. It is just the image under the converse relation, nothing else. So it is the set of all what? Of all A's from the range of the converse relation, so that there exists some B, where B is an element of X, and B, the converse A, or equivalently, what is the range of the converse relation?
Domain of R.
The domain of R, so that there exists some B, which comes from X, so that A, R, B. So this is informally, what is the preimage? Informally, the preimage, formally it is just the image under the converse relation, but informally it is the set of all points where from or whence some point of X is R accessible. So this is just the set of all points where from you may travel somewhere to X. Is it clear?
Yes.
But formally, the preimage is just the image under the converse relation, nothing more. And if you take, what is the domain of R? The domain is just the preimage of its range. Or it is just the preimage of any set that contains the range. Is it clear?
Yes.
At our seminar, we shall have some practice with this concept, and namely, we shall prove two basic properties about it. For whatever X, Y, and R, the image of the union is just the union of two images. And the second one, what if you take the image under the composition of R and Q? It would be what? Use your intuition.
The image of Q, composition, the image of R.
No, of course, it's not possible to take the composition of images because image is not necessarily a binary relation. It is just the image of the image in that order. Is it clear?
Yes.
We shall prove it. We shall prove it. And now, as our last statement, let's prove that, let's compute the image of the empty set. What is it? Formally, it is the set of all B's which come from the range of R, so that for some A from the empty set, we have an arrow from A to B. So what is it?
It's empty set.
It is empty, of course. For this is false. This is always false. Hence, this condition is false. So it is the set of all elements which satisfy some knowingly false condition. Of course, there is no such element. Is it clear?
Yes.
So that means that from nowhere, you may travel nowhere. Is it clear?
Yes.
Any questions, dear students?
Could you please draw a diagram for the pre-image?
Pre-image. Okay. Let's find it on a diagram. First, let's make a diagram, say, for this R. Let's use it as an example. Here we have arrows from 0 to 1, from 0 to 2. What else? From 1 to 3, from 5 to 3, and also from 5 to 4. This is the diagram for A. Do you agree?
Yes.
And now let's take the preimage of, say, the set which consists of 3 and 4. What is the preimage? The preimage, first of all, let's mark this set itself. It has 2 points, 3 and 4. And I want to find all points where from 3 and 4 are accessible. So the first coordinates of all pairs, whose second coordinate is either 3 or 4. Clearly, I may go to 4 from 5. So 5 belongs to the preimage. Is it clear?
Yeah.
Where from may I go to 3?
From 1 and 5.
From 5 and 1. Hence, that's 1. Any more points? May I come to 3 or 4 from any other point?
No.
No, so that is the preimage.
Okay, thank you.
Is it clear?
Yes, thank you very much.
It is easy to see that the preimage is the same as the image under the converse relation, which it is by the definition. So if you change the direction of all arrows, you may observe that it's possible only 1 and 5 are R converse accessible from 3 and 4. Is it clear?
Yes.
This concept is very, very easy, in fact. Just take it in the right way. So use, say, diagrams and formally use quantifiers. So this is just the set of all points where to we have an arrow which goes from x, from some point in x. Some point is rendered symbolically via the existential quantifier. From some a from x, there is an arrow. Any more questions?
No, thank you.
So thank you, dear students.
Евгений,
Ага,
можно еще раз, пожалуйста? Я не очень понял, почему
пожалуйста.
все-таки говорим, что там if and don't leave, почему мы доказываем только в одну сторону?
Ага. Ну, мы не доказываем только в одну сторону. Но смотрите, давайте вообще, как доказать, что одно множество равно другому?
Что они оба подмножество другого.
Да, но ведь по определению мы можем так сказать. А равно b тогда и только тогда, когда любой x, он принадлежит А тогда и только тогда, когда он принадлежит b. Но ведь здесь две импликации. Вот эта связка, она означает, что из первого следует второе, и из второго следует первое. Но я как бы две импликации сразу и доказываю.
То есть мы как бы идем из справа налево, а потом слева направо.
Ну, мы идем и туда, и сюда. Мы говорим, что вот из этого следует вот это, и наоборот. Из этого следует вот это, и наоборот. И в результате мы получаем импликации и туда, и обратно.
То есть можно сказать, что мы таким способом просто записали две импликации?
Да, безусловно, так можно сказать. Потому что вообще логически, вот когда я говорю альфа эквивалентно, или по-русски говоря, равносильно, или еще говорят эквипалент, эквипалентно, ну это все не важно. Это просто означает то же самое, что конъюнкция двух импликаций. Когда альфа равносильно бета. Когда из альфа следует бета, из бета следует альфа. Это две импликации.
Все понятно, спасибо большое.
Пожалуйста. Еще вопросы?
Да. А domain of R, это получается
Область
множество.
определения отношения.
Ну, то есть получается множество всех во первых координат.
Да, безусловно.
Я понял.
Множество всех первых координат.
Спасибо.
Жалко, что мы не привели геометрический пример. Вот это, конечно,
А он
жалко.
будет потом?
Забыл. Ну, давайте уж сейчас прямо его и приведем. Вот смотрите, давайте бяку какой-то нарисуем на плоскости. Мы ведь можем с вами плоскость рассматривать как множество пар координат, правильно?
Да.
Вот тогда каждое множество на плоскости – это бинарное отношение. Вот совершенно любое множество, загогулину такое нарисуем, это бинарное отношение. Назовем его Q. Что тогда будет его доменом? Его доменом является просто проекция на ось абсцисс. А что будет его рейнджем? Рейнджем будет его проекция на ось ординат. То есть проекция на первую координату – это то же самое, что домен. А проекция на вторую координату – это то же самое, что range.
Я понял.
Ну почему? Потому что любая точка вот здесь, она характеризуется тем, что вот какая-то есть точка, может быть, не одна, с такой первой координатой. Понятно?
Да.
Так, был еще какой-то вопрос, пожалуйста.
Да, я хотела попросить показать еще раз domain R, то же самое равно, что range converse R. Да?
Ага! Вот такая теорема. Domain R – это то же самое, что range R в минус первый. Ну, как это доказать? Ну, смотрите, когда у нас x попадает, вот у нас А – это какое-то отношение между А и Б, правильно?
Угу.
А в минус первый, ну, соответственно, между Б и А. Значит, что значит, что x лежит в домене R? Это, ну, или R по-русски говоря, это означает, что x лежит в А, и у нас есть какой-то такой y, что из x можно попасть в этот y, по R, правильно?
Угу.
Давайте теперь напишем условие. Когда x лежит в рейнже r минус 1. Ну, рейндж r минус 1, он где? Он тоже в А, правильно?
Да.
Это значит, что x лежит в А, и есть такой y, что я могу из y по стрелке r минус 1 попасть в x. Но это же
да.
одно и то же.
Да, я поняла.
Поэтому условия принадлежности рейнджу обратного отношения и домену самого R, они эквивалентны. Ну, значит, и множество равны.
А вот в контексте image у нас это было, то есть domain R то же самое, что range image R минус 1.
Домен А это, ну, домен это что такое? Домен это прообраз рейнджа.
Я поняла.
Ну, смотрите, вот у нас есть А, у нас есть Б, да? Но реально у нас не из всех точек А ведут стрелки. Реально, может быть, не из всех. И вот у нас вот это то, откуда реально идут стрелки. Это у нас домен. Домен, да? Область определения, если мы перешли на русский язык. А вот это вот range или область значений. Вот она. Теперь смотрите, ну, что такое домен? Ну, если я возьму вот этот вот range и посмотрю, а откуда можно в range попасть? Ну, из домена только.
Да, спасибо.
Можно это формально расписать, хотя это немножко нудновато. Ну, в общем, довольно несложно, потому что, ну, когда у нас точка попадает вот сюда, да? Тогда и только тогда, когда, ну, давайте ограничимся, что мы в А там находимся для любого x из А. Значит, тогда и только тогда, когда у нас существует такой y, который попадает в range, да, и у нас из этого y r есть r-1 стрелка в x. Правильно?
Да.
Хорошо. Но что значит, что y попало в range r? Ну, это значит, у нас существует такой z, что у нас из z идет r стрелка в наш y. Тут мы можем, кстати говоря, перевернуть. Тут мы можем написать x, r, y. Смотрите, это все те и только те точки, что существует y, существует z. Я это квантор выношу, потому что вторая часть конъюнкции от него не зависит. У нас существует такой z и y, что можно из z попасть в y, и из x можно попасть в y. Ну, вопрос, когда это происходит. Когда такие y и z существуют. Ну, я утверждаю, что это происходит тогда и только тогда, когда у меня из x можно куда-то попасть. Ну, почему? В одну сторону очевидно, правильно? Тут просто содержится вот это высказывание.
Да.
И в другую сторону тоже очевидно. Почему? Ну, если я знаю, что из x я могу попасть в какой-то y, почему тогда обязательно существует z, из которого я могу попасть в y? Что можно взять в качестве z?
Y?
Да x, конечно.
Да, и
Вот, поэтому и в другую сторону очевидно. Значит, эти условия эквивалентны. А это, в свою очередь, означает, что x как раз и лежит в нашем домене. Ну, если из него можно куда-то проехать по R. Значит, домен, он равен образу, точнее сказать, прообразу рейнджа. Еще вопросы?
Евгений Владимирович, а можно, пожалуйста, пример? Вы сказали, что R-композиция R обратная не всегда...
Ну, мы на семинаре хотели такой пример привести. Ну, давайте его приведем сейчас. Ну, пожалуйста. Значит, я вот возьму такую фигню. 1, 2, 1, 3. Обратная как выглядит?
2, 1, 3, 1.
Конечно. 2, 1, 3, 1. А теперь как выглядит... Что?
Ну да, там 2 в 3 получится.
Смотрите, вот куда я могу попасть? Сначала по первому, потом
2,
по
2, 2,
второму.
3.
Ну, я могу, конечно, попасть из двойки. Куда? Обратно в двойку. Я сначала по этой паре пройду, потом по этой. То есть здесь есть ID. Но я могу попасть из двойки в единицу, а из единицы могу пойти в тройку, поэтому вот это тут тоже лежит. Из тройки я могу пойти в тройку.
И в двойку.
Но тоже я могу пойти из тройки в двойку. Вот. То есть в данном случае, смотрите, вот из тройки я иду по r в минус 1 в двойку, а затем по r я из двойки иду в, извините, в единицу. Я иду по r в минус 1, а из единицы по r я могу в двойку пойти. То есть, как видите, это не ID. Понятно это?
Да. А почему мы говорим, что R это подмножество А умножить на B? Просто потому что...
По определению. Мы говорим, что бинарное отношение А на Б – это просто любое подмножество такого Декартового произведения.
Хорошо.
Еще, пожалуйста, вопросы. Ну, похоже, что нет вопросов.
Да, я думаю, на этом вопрос закончили.
Да,
Спасибо
тогда,
большое.
дамы и господа, благодарю за внимание. Давайте с вами. Ага.
Да, у меня лишь вопрос. Вы можете файл с доской прикрепить?
Файл с доской, но вопрос в том, как вы его прочтете. Он, видите, в формате вот этой странной программы. Его надо как-то конвертировать. Я могу его прикрепить, мне не жалко. Вопрос только в том,
да,
что
я
вы
это
будете
попробую.
делать. Если вы, так сказать, матерый линуксоид, но вы просто установите... Тут есть экспорт to PDF. Ну, давайте, тогда можно. Хорошо. Вот, ладно, прикрепим. Не надо быть линуксоидом, чтобы этот файл посмотреть. Хорошо. Тогда только, чтобы я не забыл, если что, напомните мне про этот файл. Ладно.
Да, хорошо, спасибо.
Благодарю
Или вы
за
можете просто в
внимание.
Zoom скинуть.
Могу скинуть просто в Zoom, а как это делается?
Там, по идее, вот в чате прикрепить файл есть.
В чате есть прикрепить файл.
Мгм.
Так, ну давайте попробуем. Так, send файл, действительно такое есть. Так. Ага. Значит, сегодня у нас 28-е, да?
Да.
Так, ну что, прошел файл?
Так. Да, супер. Спасибо.
Ну, хорошо, пожалуйста. Вообще все это написано в моем конспекте.
Ну,
Так что-
нет, да, это просто чтобы на всякий случай.
Хорошо, пусть будет, если что.
Да.
Ладно. Ну что ж,
Спасибо.
тогда прощаемся
Спасибо
с вами.
большое. До
Дамы и
свидания.
господа,
Да, до свидания, хорошего вам дня.
До
До
свидания.
свидания.
Благодарю вам того же.
До свидания.
Спасибо, до свидания.
До свидания, дамы и господа.